So we have an expression for the expected value of x. In this case, we know that it can be written as the sum from x equals 0 to infinity of x times the probability that x is equal to x. If we write out the first few terms of this sum, well, clearly the first is 0 because x is 0. The next term is just 1 times the probability that x is equal to 1, plus 2 times the probability that x is equal to 2, plus 3 times the probability that x is equal to 3, and so on. Now you might think about trying to rearrange this in a variety of ways, but let's just try this. What we're going to do is we're going to add the terms up in a slightly different way, and to suggest how to do this, I'm going to rewrite this as follows. This is the probability that x equals 1 plus, now I have 2 times the probability that x is equal to 2, so I need to write down the probability that x is equal to 2, and I have to add it in a second time, which I'm going to do underneath, like this. So I'm starting the process of rearranging the terms. And then here I have 3 times the probability that x is equal to 3, so I can write this as the probability that x is equal to 3, plus I have to add it in a second time, plus I have to add it in a third time. And you can see, and so on, I'm going to get 4 times the probability that x is equal to 4. So what I've done is I've written down all of the terms, but I've organised them differently, and in a sense I've introduced a second dimension. This is now a table of values which I could index by an x coordinate and a y coordinate, or a double sum, which is the formal way in which we're going to approach it after we've done this. Now, this expression here is looking at this table, and it is adding all the terms up in a certain order or arrangement, which is by column. It's saying, well, let's add up the first column and we get this. Add up the second column and we get this term. Add up the third column and we get this term, and so on. And so this is a summary of how to add up the terms in the table if we add them up column-wise and write down the result for each column. Now, what we're going to do instead is to add it up by row. So we're going to write down an expression here which says, okay, I'll add up all of the terms in the first row. Now, x takes values 0, 1, 2, and so on, and here we're adding up all the probabilities apart from 0, and so if we add up the first row, we simply get the probability that x is greater than 0. If we add up the second row, we're adding up all the probabilities for x being strictly greater than 1. The only ones that are missing are 0 and 1, and so the sum of these probabilities is the probability that x is strictly greater than 1, and you can see the third row is going to be the probability that x is greater than 2, and so on, and that gives us the sum from x equals 0 to infinity of the probability that x is greater than x, which is the required result. Now, to be rigorous, of course, I need to know that I can take all of the terms and I can add them up in a different order. And I am allowed to do that if the series is what we call absolutely convergent. And a series sum an is absolutely convergent if the sum of the absolute values of the terms converges, and it's been implicit in our argument all the way through that this expression here exists. In other words, we're assuming that we're dealing with a random variable which has a finite mean. In other words, this series here converges. And the terms in here are x times the probability where x goes from 0 to infinity. So all of the terms, the an, are all greater than 0, and if the mean converges, then clearly this series converges absolutely because it's a series of positive terms. So the requirement of absolute convergence is met, and that means that I can look at all of the terms and I can add them up in any order that I like. I can add them up by the columns or I can add them up by the rows. And so this is a valid procedure. Now what's really happened here, in a sense mathematically, is that we've taken what looks like a one-dimensional sum. We've expressed the terms in a table so that they become indexed by 2 dimensions. And so we've turned a one-dimensional sum into a two-dimensional sum. And formally you can solve this by just working in that way on this sum. And the way you would start is you would say, well, the sum from x equals 0 to infinity of x times the probability that x equals x is equal to, the motivation now is, let's turn this into a double sum, try to change the nature of the expression by adding up rows instead of columns, which is equivalent to changing the order of summation in the double sum. And to make this look like a double sum, you pick on x and you say, well, x is just 1 added up x times. And so you can write this as the sum x equals 0 to infinity of, now x is, I'm going to replace x by something, and then I'm going to have the probability that x is equal to x. And x gets replaced by this. I'm going to add for y equals 1 up to x 1. Now I do have to be careful here because as soon as I've written that I see I can't go from y equals 1 to x is equal to 0. So what I really should have done is said, well, it doesn't really matter that I change that to a 1 because when I look at this sum, the first term is 0. So I can write this as the sum from 1 to infinity of those terms because the first term is 0. So really what I'm trying to rewrite is this, and that sum makes more sense when expressed that way. Now then, what you have to do formally is to work with this. This has given us the intuitive motivation, and a more sort of rigorous algebraic approach to solving this problem is to work with it this way, to turn it into a double sum by rewriting x, and then to work formally with this to get the same result. So try doing that, and when you have, come back to the next video.